Hello students, in this class we will be discussing data representation used in communication network, direction of data flow in communication network, physical structure, physical topology, categories of networks. Now how to make the network efficient? To make the network efficient, we have to understand what are those datas and how this data passes from one device to other device. So let us see data representation and direction of data flow. The data which we are transmitting in the network can be text, it can be image, audio or video. If it is text, it will represent using ASCII code. ASCII letter is represented by 7 bits for each symbol. For example, H is represented by 48. There is one extended ASCII code. In extended ASCII code, what is done, along with the 7 bit, we add one more 0 in the LSB side. So H in ASCII, extended ASCII will be 0, 1, 0, 0, 1, 0, 0, 0. Okay? But you know, the ASCII code or extended ASCII code have 8 bits. So with 8 bits, we can have maximum 2 to the power 8. That is 256 number of symbols we can represent. That is sufficient for only English language. But you know, in world, we have so many languages are there. To support that, in place of 7 bits or 8 bits, we use more number of bits. That is what is a Unicode. Unicode is having 16 bits. So this supports more languages. It cannot support all the languages in world. So to support all the languages, there is another code is used which is called the ISO, which uses 32 bits. So with 32 bits, we can have 2 to the power 32 number of symbols. So with 2 to the power 32 number of symbols, we can support all the languages in world. Whatever the symbols they are using, all can be addressed with ISO. Along with text, we also transmit images. So how image will be transmitted? Image will be also converted into binary bits. For converting image into binary bits, image is divided into matrix of pixels, and each pixel is basically a dot. Each pixel is assigned bits. Example, let us say black and white. We can represent a dot using a single bit. That bit can represent either a black or white. Assume I have a black, so for that I can say that this is a black. I can say this bit is 0. And suppose this is a white, this bit can be represented as 1. So if 1 is there, that indicates a white color. If 0 is there, it indicates a black color. If we have a grayscale, if I am using 2 bits, then we can represent 4 colors in grayscale. Let us see how. This is one color, white, then little bit darker, then little bit darker, then maximum completely black. So I can say that here this is 1, 1, 1, 0, 0, 1, 0, 0. So you understood that with 2 bits, I can have 4 colors. See, similarly, if I have 3 bits, I can have 8 colors. If I have a color image, how do you represent that? Color image is represented by a combination of 3 pixels, red, green and blue. And so a single color pixel is combination of 3 color pixels. Let us take one example. A 10 centimeter plus 10 centimeter picture is to be scanned by a scanner. This has resolution of 100 pixels per centimeter square. Each pixel can be represented in 4 bits. Find out the number of bits to be transmitted for sending the total page information. Okay, that means I have a single page here. This paper, I have to scan this paper, convert into pixels and transmit. Right? So if I want to transmit, I want to send this, what will be the total page information? Now find the number of bits to be transmitted for sending the total page information. Okay, if here we are considering 4 bits, this is the first case. Another case is if it is a standard color scanner. If it is a standard color scanner, find the total number of bits. Okay, let us understand there are 2 cases are there. First case, 10 plus 10 centimeter picture to be scanned by the scanner. Presently, first case we are considering is a black and white. Okay, and let us say the second case is color with each color representing 8 bits. Okay, let us say A, in which I have size of the paper is 10 cross 10 So 100 square cent. So 100 cm square, right? And number of pixel will be 100 into 100. That will be 10 to the power 4 pixels. Okay, we'll have 10 to the power 4 pixels. Each pixel is represented by 4 bits. So total will be 10 to the power 4 into 4 bits. If I want to transmit this paper, this image with 4 bits per pixel, and we consider it as a black and white with grayscale image, then it will be 10 to the power 4 into 4 bits will be transmitted. Now consider the second case. Second case is given us, it's a color image, and color image, and here each pixel is represented. Color image means it is combination of 3 pixels. Okay, and each pixel is here is given as 8 bits. Okay, so what will be the total number of bits? Total number of bits will be equal to number of pixel is same, 10 to the power 4 into each pixel into how many pixels will be 10 to the power 4, and every color pixel is made of 3 pixels, 3 colors, right? So that multiplied with 3 into, and every color is represented by 8 bits into 8. So this will be 240 into 10 to the power 3 bits. Now let us say direction of data flow. The direction of data flow can be 3 possibly: simplex, in which data transfer in one direction. So you can say here's the mainframe's computer, direction of data flow is this direction. Okay. And another is half duplex, in which it can be transmission can be both direction. Data transfer in both direction, but not in the same time. Let us say A, this is B. So at a time from A to B will be transmitted, or B to A will be transmitted. But as it is half duplex, it will not be simultaneous. Okay. Next is a full duplex. In full duplex, data transfer in both direction simultaneously. So this is what is the case transmission. So at a time, at same time, from A to B is possible, as well as B to A will be possible. That is the full duplex. Let us take some examples. In our house, we use remote control. That is case of simplex. Only we from remote control will be transmitted to the TV. TV cannot send signal to remote control. Next is half duplex walkie-talkie. In walkie-talkie, they speak something and then tell over. After that, the other person will speak something and then tell over. That is what an example of half duplex. Our telephone conversation, if you see, that is an example of full duplex. Okay, we want to make the network efficient. To make the network efficient, we should know what are those data. We understood that data is basically in binary form, whether it is a text, image or video. Then how these devices are interconnected, that we will be discussing. So to understand that, we have to understand the physical structure. There are types of connection between two devices, network topology, and categories of network. These are the things we will be discussing. Now we will be discussing the physical structure. Type of connection between two devices. We can have point-to-point communications, which provides a dedicated link. So you can see here, these are the two workstations. This is one workstation and this is another workstation. And there is a single link. So they will be communicating point-to-point. The other case is multi-point connection, in which more than two specific devices share a single link. You can see here there is a mainframe and there is a link. This link is used by multiple workstations. So this is shared. Now we will discuss the physical topology. It is the geometric representation of all the links and linking devices. So there are different topologies are there. First is the mesh topology, in which every device has a dedicated point-to-point link to every other device. Here if you see, there are 5 devices are there: A, B, C, D and E. Every device A is connected to E, A is connected to B, A is connected to C, A is also connected to D. Similarly, if you see D, D is connected to E, A, B, C. What will be the advantage? Advantage is the dedicated link, privacy. So if A is transmitting to D, B, E, all other people cannot see. Easy to identify any fault. But disadvantage is that the number of links required will be much large. In this network, how many links are required? It will be 5 into 4 by 2. That is n which is equal to 10. The formula is n into n minus 1 by 2. Okay. Now let us consider we have a university. There are 5,000 students are there. Students, faculty, all including 5,000. So for 5,000 students, what will be the number of links required? 5,000 into 5,000 minus 1. Let us say approximately 5,000 by 2, which will be coming to be 5,000 into 2. So 125 into 10 to the power 5, this many number of links are required. If we'll have this many number of links in a campus, I think we'll not have any space to work. Okay, so that's how the mesh topology is fine. If we have a very small network, 4 or 5 computers, that is okay, but it is not, beyond that it will not be acceptable. Okay, this happens the large number of links required. Next is the star topology. In star topology, each device has a dedicated point-to-point link only to a central control using a central hub. Let us see here, this is a central hub to which this device, this device, this device, these devices are connected. Advantage is less expensive than mesh, but still not a good solution. Why? Consider we have a big campus and the hub is present at the main office, and all the hostels are maybe 400 meter away, 500 meter away, 1 kilometer away, 5,000 students are there. So we have to lay 5,000 cables from the main office to each student's room, which is not a good solution. So then what can be done? We can use tree topology. In tree topology, what is done? Majority of the devices are connected to a secondary hub, that in turn connected to a central hub or switch. Generally what is done, let us say this is what is the topology. This is the switch. Let us say this is at the main office, Institute Computer Center. Okay, this is ICC Institute Computer Center, and this is, let us say, one hostel. Okay, this is one hostel 1, this is hostel 2. So what we can do from this hostel, let us say, accommodating 500 students. This hostel is accommodating another 500 students. Okay, now H1, so we can have a single line connecting to H1. We can have that H1 will support to 500 students. So from this hub, we have star topology in which we will be connecting to each of the students. From hostel 2, we can connect to around 500 students from this hub. Okay, so from the main office, we will be requiring only one line here, one line here. So suppose I have 10 hostels, so I can say that 10 such lines will be accommodating 5,000 students. Okay, next is the BOS topology. In this, one long cable acts as a backbone to link all the devices. This is what you can see. This is the BOS. And to this BOS, different devices are connected. Any communication has to pass through this main BOS. This main BOS has generally have higher capacity, larger bandwidth. It can transmit at higher speed. Advantage is easy for installation, less cabling, but disadvantage is that if this cable is getting out of order, then complete communication will be disrupted. Difficult fault isolation, reflection at tap can degrade the quality of the signal. So here we are connecting, here also we are connecting these connections. Because of that, there can be a reflection. So that will create signal strength reduction. Okay, that will degrade the quality of the signal. A fault in the backbone stops all transmission. Just I discussed that. The next is the ring topology. Here, each device has a dedicated point-to-point line configuration only with the two devices on either side of it. You can see here, this device is connected to this device and this device. Let us say this device is connected to this device and this device. The advantage is that each device acts as a repeater. So repeater means it will be regenerating the signal. But here the n number of cables need for n device. So there are 5 number of devices. So 5 cables will be suitable to make the ring topology. To add extra, what I have to do, I have to remove this cable. Suppose I want to add one more device here. So what I shall do, I shall connect here, and this cable I shall connect here. So this will be removed. Okay. So one more cable I can use and make the ring topology. And in case there is a problem, we can find out, okay, up to where is the problem, we can identify. So fault isolation is also simple. Next is hybrid topology. It can be combination of all the topologies. Let us say this is our Institute Computer Center, from which this is going to hostel H1. Okay, so here I can have a hub, from which I can have another hub. Here number of devices are connected. This can be also connected to another ring topology. It is also possible. Okay, it can be connected to another ring topology. So this is a combination. This typically considered as a hybrid topology. Okay, let us see the categories of network. Based on the size of the network, we can have 3 types of networks. They are called as a local area network, metropolitan area network, wide area network. So if we have a small campus, or we can say that small or big campus, inside the campus all the connection is considered as a local area network. If I have a university, all the devices, all the computers are connected, that is called as a local area network. Assume one university is having multiple centers in a city. Let us consider big city. In big city, let us say Hyderabad is having 3-4 centers. So we want to connect them. That is called as the metropolitan area network. Example of local area network, in which in small area all these devices are connected. In this case, we have one building here, another building here, another building here. These buildings are far away, but all of them are inside a city. In a metro city, these buildings are there. They are connected. So it is a metropolitan area network. Other cases in which the centers are far away, they are present in different countries, and they are connected. That is called as the wide area network. 3 types of networks. One is local area network, second is a metropolitan area network, third is wide area network. Thank you.